Hey guys, today we're going to imagine something that has haunted human curiosity for as long as we've looked up at the stars. What if we could move faster than light itself? You're lying there, maybe in the quiet dark of your room, the hum of the world fading just a little, and you picture a single beam of light, bright, pure, racing outward at 299,792 kilometers per second. For over a century, that number has been something like a sacred law of nature.
Nothing can catch up. Nothing can overtake it.
Yet somewhere deep inside us, there's always been that question, what if? You close your eyes and imagine yourself inside a ship, silent, sleek, its surface glowing faintly like moonlight on water. It's hovering at the edge of our solar system beyond Neptune, where sunlight is no longer gold, but a cold, thin whisper. Out there, you fire up the engines, not to travel through space, but to push against the limits of reality itself. For a moment, the idea feels intoxicating. The vast distances that trap us and the 4.3 light years between us and Alpha Centauri, the 2.5 million to Andromeda, would collapse into minutes.
Messages could cross galaxies.
Civilizations could finally meet, and the story of humanity, so long confined to one fragile world, would finally open wide. But before we chase that dream too far, it's worth pausing. Because to move faster than light isn't just a technical problem, it's a philosophical one. It asks what it means for something to move, to exist, or to even experience time. Einstein once described the universe not as a stage where things happen, but as a woven fabric of space and time. An invisible texture where every event, every particle and every photon are connected by geometry. Inside this geometry, light doesn't simply move, it defines the shape of reality itself. Imagine that fabric as an endless ocean. You and I, every planet, every atom, we're like small ripples moving through it. Light is the fastest ripple possible, the crest that moves across the sea with perfect precision. To move faster than light would mean making a wave sharper than the sea itself, breaking the rules the ocean is built upon. Still, humans are not easily satisfied by impossible. We've always stared at the edge of things and asked if there might be another way. Could we perhaps bend that ocean instead of trying to swim through it? Could space itself be stretched, twisted, folded, so that instead of moving faster than light, we simply shorten the distance? It's an idea both simple and extraordinary, and yet it carries consequences far stranger than we might expect. If time and space are linked, then to move faster than light would also mean to move sideways through time. You might leave Earth today and arrive before you even departed. You could see the stars not as they are, but as they will be. You might even meet your own signal coming back from the future. There's something hypnotic about thinking this way. To imagine light not as a limit, but as a doorway. For centuries, thinkers from ancient philosophers to modern physicists have wondered if our universe might allow such a loophole. If somewhere in its deep geometry there are tunnels, folds, or invisible shortcuts. And in those quiet moments when the night sky feels too big, it's easy to feel small. But then you remember, even the speed of light, that cosmic boundary, is a kind of invitation. It marks the horizon of what we know, and beyond it lies what we might yet imagine. Tonight, we begin a journey not of engines or coordinates, but of thought, through the realms of physics, imagination, and philosophy. Take you to ask, if we could go faster than light, what would that mean for everything we understand about space, time, and ourselves? Wherever you are, let the world slow down for a while. Soften your gaze. Let the hum of life around you fade and gently drift with us into tonight's quiet exploration. The moment we start asking what it would mean to move faster than light, one name inevitably rises like a quiet constant in the night: Albert Einstein. Einstein didn't just change how we think about speed, he changed what speed actually means. Before him, motion was simple. If a car moves faster than a bicycle, it catches up. If a bullet moves faster than sound, it breaks the barrier and creates a boom. Why couldn't something just move faster than light? Einstein's answer was both elegant and unsettling. He showed that the universe isn't built like a racetrack. It's more like a web of relationships. Everything, space, time, matter, light, is woven together in such a way that when one changes, all the others must shift to keep balance. And light, he discovered, was the ultimate reference point. No matter how fast you move, light always outruns you at the same speed, 299,792 km/s. You could chase a beam with the fastest rocket imaginable, but from your perspective, it would still pull away, unchanged. This wasn't a flaw in mathematics. It was a glimpse into the structure of reality itself. To make sense of it, Einstein redefined motion. When you go faster, time slows down for you. Space itself contracts. Clocks tick differently, rulers shorten. To maintain the universe's internal balance, the cost of approaching light speed is enormous. You begin trading time for motion. You might picture a spaceship nearing that limit. From the outside, it's blazing across the void, its engines screaming with energy. But inside, something strange happens. The crew moves slowly, their voices stretch, the clock on their wall seems to freeze. To them, everything feels normal. But to the rest of the universe, their journey has bent time itself. Now imagine pushing even further, faster and faster, until you approach the speed of light. The closer you get, the heavier you become, the more energy you need. And at the very moment you try to match that sacred number, light speed, the math
breaks, your mass would become infinite, your time would
stop. Your energy requirement would grow beyond all the power in the universe. That's why physicists often call the speed of light the cosmic speed limit. It
isn't a suggestion that it's the boundary condition of existence. You can think of it like the edge of a map drawn in fog.
Beyond it, our equations simply dissolve. But Einstein's theory also left a tantalizing clue, an almost poetic loophole. It didn't forbid space itself from changing faster than light. It only said that nothing within space could travel that way. And that distinction changed everything, because if light speed is the fastest, you can move through the universe.
Maybe the trick is not to move through it at all.
Maybe you could move the universe itself. That simple thought, the idea of bending, stretching, or compressing the very stage of reality, would later inspire some of the most extraordinary ideas in modern physics: warp drives, wormholes, quantum shortcuts. But before we go there, it's worth pausing on something more human. Why does this question, what if we could go faster than light, matter so much to us? Perhaps because it touches something deep, our longing to reach beyond limits, to connect across distance, to defeat the silence of the cosmos. The speed of light isn't just a number, it's a mirror. It reflects our hunger to explore, to understand, to not be bound by the cages of what we know. And yet, the irony is that the very law that frustrates us, the one that says no faster, is also the one that makes the universe coherent, stable and beautiful. Without that limit, cause and effect would dissolve. The future could ripple backward into the past. Stars would flicker in chaos. And the night sky, instead of being a quiet map of light from ancient times, would be a storm of collapsing timelines. So maybe, for now, the speed of light isn't a wall. It's a guardian, holding the story of reality together until we're ready to understand what lies beyond it. Still, That doesn't stop the dreamers, the engineers, and the physicists from asking, what if we could bend the rules instead of breaking them? Because sometimes the way forward isn't through speed, it's through imagination. Close your eyes for a moment and imagine that space and time are not two separate things but one, a single unified fabric stretching endlessly in every direction. Soft, invisible, and yet powerful enough to cradle galaxies. This is the space-time Einstein revealed to us, and everything that exists, from the smallest atom to the largest galaxy cluster, dances upon it. In this cosmic tapestry, nothing truly moves the way we think it does. When a planet orbits a star, it isn't being pulled by gravity. Instead, the star bends the very fabric around it, and the planet simply follows the curve. Imagine rolling a marble around a stretched sheet of fabric where a heavy ball sits in the center. The marble spirals naturally toward it. That's gravity, not a force, but a path through curved space. And here's where things get strange. Light too follows those curves. When it passes near massive objects like black holes or galaxies, it bends. Not because something grabs it, but because space-time itself is warped. In fact, this warping is how we discover dark matter. Astronomers noticed galaxies bending light more than visible matter could explain, hinting at invisible mass lurking everywhere. So, what does this mean for traveling faster than light? It means that space itself can stretch or squeeze. And when it does, distances change without anything technically moving. Think of the early universe.
Right after the Big Bang, in the first fraction of a second,
The fabric of space expanded faster than light, not because particles were racing through space, but because space itself was inflating. In that moment, regions that were once connected drifted apart faster than light could ever travel. This tells us something profound. The universe already knows how to go faster than light. We just don't know how to ride that wave. You might picture it like this. Imagine drawing two dots on a balloon. If you blow air into the balloon, the dots move apart. But they aren't traveling through the surface. The surface itself is expanding. That's how galaxies move away from one another as the cosmos grows. Now, if one could control that expansion, compressing space in front of a ship and stretching it behind, the craft wouldn't technically violate Einstein's rule. It would stay still, floating in a bubble of space-time, while space itself did the moving. This is the seed of the warp drive concept, an idea that sounds like science fiction, but is born from the very logic of relativity. The math even works, almost. But before we leap ahead into the details of bending space, let's dwell a little longer on what space-time feels like. Because though it sounds abstract, it shapes every moment of our lives. When you drop a ball, when the moon raises the tides, when the earth spins gently beneath a sunbeam, all of that is geometry. The floor beneath you, the seconds ticking away, the breath you take, they're part of a vast choreography playing out inside this invisible web. And this web isn't flat or still.
it ripples.
When two black holes collide, they send tremors through space-time, gravitational waves, ripples that stretch and squeeze the universe itself. We can now detect them faint and slow, like the heartbeat of the cosmos. It's humbling, isn't it? The idea that every heartbeat, every star, every motion happens within a living, moving ocean of space-time. And if we ever wish to travel faster than light, we'll have to learn to surf that ocean. Not by breaking through it, but by shaping it. But such mastery would come with a cost. Because the moment we begin bending space and time, we also bend causality and in the order of events, the story of before and after. And once that order begins to blur, reality itself starts to tremble. When we start talking about moving faster than light, we're not just flirting with speed. We're tampering with the foundation of reality itself. Because in Einstein's universe, time and causality, the sequence of cause and effect, are deeply intertwined with motion. Change one and the others begin to unravel. Imagine this. You send a signal to a distant star faster than light. To you, it's just a message, a pulse of data or energy arriving almost instantly. But for someone watching from another reference frame, perhaps someone moving differently through space, your signal could appear to arrive before it was sent. That simple act, pressing a button, sending a pulse, could make you, in their eyes, the effect of something that hasn't even happened yet. Cause and effect reversed. Reality untangled. It sounds absurd, doesn't it? Yet it's a logical outcome of relativity's geometry. When information moves faster than light, different observers can no longer agree on what happened first. Time, usually a one-way river, begins to split into whirlpools and loops. You can think of it like drawing a timeline on paper, a clean, straight line from left to right. Now bend the paper until the line crosses itself. Suddenly, events that were once separated are neighbors. The beginning meets the end. You've just created a causal loop. In such a loop, you could send yourself a message from the future, or worse, prevent your own message from ever being sent. The paradoxes pile up quickly. It's the same family of thought experiments that gave us the grandfather paradox. If you went back in time and prevented your grandparents from meeting, would you erase your own existence? Physicists call these outcomes violations of causality. Nature, as far as we can tell, hates them. The universe seems to enforce its timelines with quiet, relentless discipline. And light speed is the gatekeeper of that order. To truly grasp why, picture space-time not as something flat, but as layered. Every event you've ever experienced is like a bead on a string connected by light. The light from your past defines your present. The light you emit now, from the glow of your screen, the reflection in your eyes, becomes part of someone else's future. Faster than light motion would tear those strings. You'd be plucking beads from one thread and placing them on another, creating impossible stories, events with no consistent order, no shared truth. And yet, this thought that reality itself might bend under certain conditions has always been irresistible, because for every paradox, there's also a glimpse of something deeper. The idea that time isn't as rigid as we think. Consider black holes. Deep inside them, time and space trade roles. Time behaves like space, and space behaves like time. What was once forward becomes inward. What was distance becomes duration. The light can't escape, not because it slows down, but because the structure of space-time itself curves so steeply that outward no longer exists. If gravity can twist reality that much,
Might there be a way to use it, to reverse it, to create paths where light's rules no longer apply?
that's the line of thought that leads us to warp drives, concepts that don't violate Einstein's equations, but rearrange them. Instead of moving faster than light through space, you move space faster than light around you. Imagine sitting in a bubble, still, silent, untouched, while the universe slides past outside. You wouldn't be breaking the law of light speed because you wouldn't technically be moving. The space in front of you would shrink and the space behind would stretch. You'd be surfing a wave of space-time itself. But before we rush into that elegant dream, it's worth acknowledging something both humbling and beautiful: the speed of light. That unbreakable rule isn't just a barrier.
It's the rhythm of the cosmos.
It gives order to every heartbeat, every orbit.
Every sunrise we've ever seen. Without it,
There would be no before or after. Only chaos. A storm of moments with no meaning. So if we're to ever transcend that boundary, We must do so with care, not by shattering the rule, but by learning the language the universe uses to write it. The dream of moving faster than light often begins with one word whispered through both science and fiction: warp. It doesn't mean brute force, not rockets or engines that scream against resistance, but something subtler, almost poetic. To warp space is to reshape the very fabric of existence itself. Let's return to that ocean analogy for a moment. Imagine you're floating on the surface of a vast sea. The waves ripple outward in all directions. They are like light, carrying information at a fixed speed. If you could somehow create a current, a bubble in the water that moves the ocean itself, you wouldn't technically be out swimming the waves, and the waves would be carrying you. That's the foundation of the Alcubierre drive, proposed in 1994 by Mexican physicist Miguel Alcubierre. Inspired by Einstein's general relativity, he asked, what if a spacecraft could contract space in front of it and expand space behind it? The ship would ride this distortion like a surfer on a cosmic tide, gliding across space-time faster than light without ever locally exceeding light speed. It's a concept that feels like magic, but it's written directly in Einstein's own equations. At the heart of it lies a simple idea. In general relativity, nothing forbids space-time itself from expanding or contracting at any rate, even faster than light. When Alcubierre first published his paper, it caused an uproar. The equations worked. The math checked out. For a moment it seemed like humanity had glimpsed a legitimate loophole, a way to cross the stars not by force, but by geometry. Here's how it would look. A ship sitting quietly inside a bubble of untouched space-time, a region of complete stillness where passengers feel no acceleration. Around it, space itself curves like a wave, pushing the bubble forward. It's not motion in the traditional sense, more like surfing reality's own tide. Inside the bubble, everything behaves normally: light, clocks, even coffee cups. But outside, to an observer, you would appear to move faster than light, covering vast interstellar distances in moments. Sounds like something from Star Trek, right?
And that's no coincidence.
Alcubierre himself admitted the idea was inspired by science fiction, by Captain Picard's Starship Enterprise warping across the galaxy. But the remarkable twist is that relativity didn't forbid it. Still, the universe always exacts a price for bending its rules. And in this case, the price is energy. More energy than humanity could ever dream of. The equations demand what's known as negative energy density, exotic matter capable of bending space-time inward. We've never observed such matter directly. Some quantum effects, like the Casimir effect, hint at it, regions of vacuum where energy dips below zero. But producing enough to move a ship would require the power of entire suns. Even worse, the warp bubble has terrifying side effects. As it moves, it collects stray particles and radiation at its front, compressing them into a deadly wave. When the bubble stops, all that energy would explode outward, enough to vaporize anything in its path. For now, the Alcubierre drive remains a beautiful impossibility, a piece of math balanced delicately between science and dream. But in the silence of deep thought, it's hard not to wonder, could there be another way? Because the equations themselves whisper something profound, that space isn't fixed. It can be stretched, curved, folded. If one day we find a form of energy or a deeper understanding of quantum fields that lets us shape it safely, the stars might no longer be out of reach. Until then, the warp drive remains a thought experiment, a kind of cosmic poetry written in the language of Einstein. And in its quiet beauty, it reminds us that speed isn't everything. Sometimes the key to going farther lies not in pushing harder, but in reimagining what distance means. Of all the barriers between us and the dream of faster-than-light travel, none feels heavier than energy. Even the most elegant equations cannot escape the laws of conservation. The universe demands a price for every distortion, and that price is staggering. Let's start with something familiar. When you double the speed of a car, you don't just need twice the energy, you need 4 times as much. That's because kinetic energy scales with the square of velocity. Now stretch that principle to near light speeds. As a ship accelerates closer and closer to the limit, its mass, from the viewpoint of an outside observer, seems to increase. Each fraction of a percent closer to light speed demands exponentially more energy. At 90% the speed of light, you need 10 times the ship's rest mass energy.
At 99%, 100 times more.
At 99.99, the numbers spiral into absurdity. By the time you'd reach the final decimal, you'd require more energy than the sun will ever produce in its lifetime. It's as if nature set a toll booth at the edge of light speed and charged infinity. Now, warp drive theory tries to step around that toll by not moving through space. Yet even that path is steep. Alcubierre's original calculations suggested that to move a modest-sized spacecraft, you'd need an amount of negative energy equivalent to the mass energy of the entire observable universe. Later refinements reduced that to the mass of Jupiter, then perhaps the mass of a small planet. But the scale remains unthinkable. To grasp what negative energy even means, imagine the fabric of space as a stretched sheet. Ordinary matter pushes down, curving it like a heavy ball. Negative energy would do the opposite. It would pull up, creating a hill instead of a valley. That's the kind of curvature you'd need to expand space behind your ship and contract it ahead. In quantum physics, tiny flickers of negative energy do occur. Between 2 perfectly smooth metal plates placed close together, the vacuum itself produces a faint pressure difference, the Casimir effect, where virtual particles briefly exist and annihilate. For a moment, the region between the plates has slightly less energy than the surrounding space, but the amount is microscopic, detectable only with sensitive instruments. Now imagine scaling that up to cosmic proportions. Some theorists, like Harold White at NASA's Eagle Works laboratory, once suggested clever tweaks that could reduce the energy demand even further, perhaps to the level of a few tons of matter converted entirely into energy. That's still impossible for us, but tantalizingly less impossible than before. Others wonder if nature already hides sources of negative energy around black holes, within quantum fields, or in the mysterious force driving the universe's expansion, dark energy.
Maybe, just maybe, the key lies there. Still, every solution seems to come with a shadow.
A warp bubble large enough for a human might collapse violently the moment it's formed, or it might create a horizon, a one-way boundary like a miniature black hole, sealing its occupants away from the outside universe. Time inside and time outside might desynchronize completely, and yet, in the face of all that, the dream persists. Because energy, too, has always been a problem we learned to solve. There was a time when flying seemed to require impossible power. So did splitting the atom or sending signals through empty air. Every century, humanity finds new ways to coax the universe into cooperation. Perhaps one day, the same ingenuity that turned sand into silicon and moonlight into power will find a way to tap the vacuum itself, to draw from the hidden tension in space-time. Until then, the energy problem stands like a silent mountain. But mountains, as history shows, are invitations. Because for every limit the cosmos presents, there's a quiet voice that asks, what if that limit is only temporary? If warp drives stretch space, then wormholes aim to fold it, to make 2 distant places touch, It's a concept both ancient and new, as old as mythic doorways and as modern as quantum geometry. Imagine space not as an infinite flat sheet, but as a flexible fabric you can bend. If you fold that fabric until two distant points meet, then pierce a tunnel through, you've created a wormhole, a shortcut through space-time itself. The idea was born from the mathematics of general relativity. In 1935, Einstein and his colleague Nathan Rosen were exploring solutions to Einstein's equations when they stumbled upon a peculiar shape, a bridge connecting two regions of space-time. They called it an Einstein-Rosen bridge, though the name wormhole came later. To picture it, think of a black hole, but instead of ending in a singularity, a dead end, it opens somewhere else entirely. At least, in theory, a wormhole could link one galaxy to another, or even two universes. One mouth might float near Earth, the other near the Andromeda Galaxy, 2.5 million light-years away. Step through and you'd arrive instantly, without ever breaking the light speed limit. Space itself would simply be shorter for you. But as always, the cosmos guards its mysteries carefully. The math that describes wormholes also reveals their fragility. A natural wormhole, if it exists, would collapse almost instantly, faster than light itself could travel through. To hold one open, you'd again need negative energy, that elusive exotic matter capable of counteracting gravity's crush. Without it, the tunnel would pinch shut in a flash, destroying anything inside. Still, physicists like Kip Thorne, the same one who advised on Interstellar, have shown that such a structure could, in principle, be stable if threaded with enough negative energy. In that film, the wormhole near Saturn was depicted beautifully. A perfect sphere, shimmering and reflective, like a glass marble floating in the void. Entering it wouldn't feel like falling into a hole, but gliding into a sphere of distorted light. Inside, space and time would twist in strange ways. You might see stars looping around you, their light bending backward. The journey could take no time at all from your perspective, but decades might pass outside. Some versions of wormholes could even allow travel not just across space, but across time. Enter one mouth and exit in another century. Of course, that leads us straight into paradox. What happens if you return before you left? Could you send yourself a message that prevents your own departure? Once again, causality quivers under the weight of imagination, and yet wormholes remain one of the few theoretical models of faster-than-light travel that doesn't explicitly violate relativity. They don't require you to move faster than light, only to take a shortcut through a geometry where distance itself becomes a suggestion. You can almost picture it, drifting in a quiet spacecraft, watching as the mouth of a wormhole opens like a black pearl against the stars. The edge ripples faintly, a sphere that reflects the entire universe back at you. For a moment, the stars bend inward, drawn into the hole's reflection. And then, in an instant, you're somewhere else. The galaxy behind you has vanished and a new one unfolds before your eyes. Scientists have searched the sky for any sign of such structures. Strange gravitational lensing patterns, repeating quasars or duplicate galaxies, anything that might hint at cosmic tunnels connecting the universe. So far, there's no solid evidence. But the mathematics remains stubbornly beautiful, whispering that perhaps, somewhere in the tangled depths of space-time, such pathways exist, silent, invisible, waiting, and if they do, perhaps they're not empty corridors, but cosmic veins, channels through which information, energy, or even consciousness might one day flow. Because what makes wormholes so captivating isn't just the idea of travel. It's what they suggest about reality itself, that distance, separation and time might all be illusions of perspective, and that every point in the universe might already be touching. If only we could see the folds. If wormholes and warp bubbles belong to the realm of geometry, then the next path toward faster-than-light travel takes us into the world of quantum mechanics, a place where rules dissolve and probability becomes the language of existence. Here, particles blink in and out of being, appearing where they shouldn't, tunneling through barriers they can't possibly cross. And if there's any domain in physics where impossible starts to tremble, it's this one. Let's start with the phenomenon known as quantum tunneling. Imagine a tiny particle, say an electron, trapped behind an energy wall. In classical physics, it can't pass unless it has enough energy to climb over. But in the quantum world, the electron behaves both as a particle and a wave, and that wave doesn't stop at the barrier. It fades into it and sometimes, just sometimes, reappears on the other side. To an outside observer, it's as if the electron has simply teleported, moving faster than light without ever crossing the space in between. Of course, in reality, it doesn't break relativity. What happens is subtler. The wave function that describes its probability leaks through the barrier, and measurement reveals it arrived instantly. Still, the effect is real. Quantum tunneling powers the nuclear fusion in stars, allowing protons to fuse even when they shouldn't have the energy to overcome their mutual repulsion. Without it, the sun wouldn't shine. Life itself depends on a loophole in probability. That same principle fuels dreams of faster-than-light communication. Could we use tunneling to send information instantly? So far, no. When physicists tried, they found that while the appearance of superluminal motion exists, the actual signal, the transfer of information, never exceeds light speed. Nature still guards causality, even in its strangest corners. Then there are tachyons, hypothetical particles that always move faster than light. The name comes from the Greek tachys, meaning swift. If they exist, tachyons would be eternal. Runaways, they could never slow down enough to reach light speed, just as ordinary matter can never accelerate fast enough to reach it. They would live perpetually in the domain beyond the barrier. Mathematically, they emerge as curiosities, solutions to certain equations that hint at negative mass or imaginary time. If such particles were real, they might reverse cause and effect. Their motion through time would appear backward to us. A tachyon emitted now could be detected before it was even created. The idea is both thrilling and unsettling. It suggests a universe where time is not a single arrow, but a woven fabric of overlapping threads, some moving forward, some backward, all intersecting in ways our senses can barely comprehend. But every attempt to harness this for communication or travel runs into paradoxes. Signals moving faster than light could send messages into the past, destroying consistency. And the mathematics, while intriguing, often collapses into instability, the kind of runaway feedback that nature seems designed to prevent. Still, the allure of these concepts remains. Quantum entanglement, for example, offers another glimmer of strange connectivity. When two particles become entangled, they share a quantum state, no matter how far apart they drift. Measure one, and the other responds instantly. Einstein called it spooky action at a distance. It's tempting to think of this as faster-than-light communication, but it isn't. The instant correlation doesn't transmit usable information. It's a dance choreographed by shared quantum history, not a message sent through space. Yet the feeling it gives, that separation might be an illusion, keeps haunting us. Maybe space and time aren't obstacles to overcome, but emergent properties of something deeper, a cosmic network where every point already touches every other. If that's true, then Faster-than-light travel might not mean breaking physics at all, but learning to navigate this hidden structure, to move through information rather than distance, through resonance rather than propulsion. In that sense, the dream of superluminal travel may already be part of the universe's design, glimpsed in the flicker of entanglement, the hum of quantum fields, and the faint whisper of particles that refuse to obey ordinary logic. Because beneath the laws we understand lies something even more mysterious, not chaos, but connection. And if one day we learn how to follow that connection, the speed of light might no longer be a wall, but a window. Now let's step inside the dream itself. Close your eyes and imagine, just for a moment, that humanity has done it. We've found a way to go faster than light. The energy barriers have fallen, space-time bends like silk under our fingertips, and a small craft floats quietly beyond the edge of the solar system. Inside, you're weightless, calm and steady, watching the universe change before your eyes. The countdown begins. The engines hum not like rockets but like a heartbeat, a soft resonance tuned to the very vibration of space itself. Then, with a gentle shimmer, reality begins to stretch. At first, nothing seems to move. But then the stars outside begin to bend. Their light compresses in front of you, glowing bluer and sharper, while behind you it reddens, fading toward invisibility. The universe seems to wrap itself around your ship like liquid glass. You are no longer moving through space. Space is moving around you. The bubble holds steady, silent, while the distance between you and the stars collapses. The Milky Way, once so vast, begins to flow past like a river of light. Time inside feels normal. Your hands, your breath, your heartbeat, all steady. Yet outside, ages unfold, planets revolve, stars are born and die in a flicker. Light itself can't keep up. You've stepped beyond its rhythm, into a domain where the ordinary rules of experience unravel. As your craft glides forward, colors twist and distort. The constellations you knew blur into streaks, then dissolve completely. Ahead, darkness deepens. Not the absence of light, but something denser, like the unlit side of existence. If you look closely, you might see the past. Light from stars long dead still travels, slower than you. It reaches you as ghostly echoes, a record of what once was. In faster-than-light motion, you overtake that ancient starlight, watching the universe rewind before your eyes. Galaxies spin backward, supernovas collapse into silence, and distant worlds unform from clouds of dust. You're not just outrunning light, you're outrunning time itself. But then, something curious happens. As you move faster, the universe ahead seems to fade. The photons can't reach you, there is no incoming information. The blackness grows absolute, pure, formless, without direction. Physicists sometimes describe this as the causal horizon. When you exceed the speed of light, you slip beyond the region of space-time that can communicate with the rest of reality. You exist outside the universe's conversation. It's quiet there, impossibly quiet. No light, no sound, only the vibration of your own consciousness against the void. For a moment, you might feel like a god, omniscient, untethered, free from the ticking clock of existence. But then the loneliness hits. You realize that in escaping the speed limit, you've also escaped meaning itself. There's no up or down, no before or after. just a suspended now, infinite and featureless. Perhaps this is what physicists mean when they say faster-than-light travel breaks causality. Not just in equations, but in experience. Without cause and effect, without light to mark change, even thought begins to lose its sequence. And yet, even in this silence, there's awe. You are seeing the universe as it truly is, not as light shows it, but as geometry, vast and eternal. Eventually, you slow. The warp bubble fades, the stars reappear, trembling softly as if awakening from a dream. The colors settle, the hum of reality returns. You glance at the clock. It shows only minutes past, but when you radio Earth, there's no reply. The planet still exists, blue and bright, but its continents are unrecognizable. Millions of years have passed. The light you see is ancient history. You've crossed not just distance, but epochs. And for the first time you understand, to go faster than light is not merely to travel. It is to rewrite the meaning of time itself. The human mind can barely hold such a thought. Yet even here, drifting among stars that no longer know your name, there's wonder. Because every great dream begins at the edge of what seems impossible. And sometimes, the journey matters more than the destination. Now that you've glimpsed what it might feel like to travel faster than light, it's time to face the shadow behind that dream, the paradox of time itself. Einstein's equations, so elegant and complete, tell us something strange. The faster you move, the slower time flows for you. At the speed of light, time would stop entirely. And if you could somehow exceed that speed, the equations flip inside out. Time doesn't just slow, it reverses. Let that sink in. To move faster than light is to move backward through time. This isn't science fiction flourish, it's a direct consequence of relativity's geometry. For an object moving beyond the light barrier, the order of cause and effect would reverse. Events that were once the future could become the past. You could, in principle, arrive somewhere before you left. At first, it sounds exciting. A built-in time machine, a chance to rewrite mistakes or revisit history. But once you dig deeper, the beauty twists into something unsettling. Because if time can loop backward, logic itself begins to crumble. Physicists call this the tachyonic paradox, named after those hypothetical, faster-than-light particles from earlier. If a tachyon could send a message into the past, someone could receive that message and act on it in a way that prevents it from ever being sent. The universe, caught in contradiction, wouldn't know which version to choose, the one where the event happened or the one where it didn't. To prevent such chaos, reality seems to enforce a quiet rule known as causal consistency, a cosmic safeguard that keeps the timeline intact. It's as if the universe whispers, "You may imagine the impossible, but I will only permit what makes sense." Still, physicists have toyed with the idea that time travel, or time reversal, might be possible within certain limits. Wormholes, if stable, could act as closed time-like curves, pathways through space-time that loop back on themselves. If one mouth of a wormhole experiences time differently, say accelerated by gravity or near-light travel, then connecting them could theoretically let a traveler step from one era into another. But the paradox remains. What would stop someone from using that loop to alter the past, to erase the journey that created it? Stephen Hawking offered a solution with his chronology protection conjecture, a poetic name for a practical idea. It states that the laws of physics themselves will always conspire to prevent time travel on macroscopic scales. Wormholes would collapse.
Negative energy would destabilize.
Quantum fluctuations would flood the loop with radiation, destroying the path before it could be used. In other words, the universe has a self-defense mechanism against paradox, and yet there are cracks in that armor. Quantum mechanics allows for tiny, fleeting violations of causality, moments where effects seem to precede their causes, measurable only at the smallest scales. Some experiments even suggest that particles can influence each other across time. Retrocausality, as if the future can nudge the past in subtle, probabilistic ways. If that's true, perhaps time isn't a single arrow after all. Maybe it's a tapestry, threads running in both directions, weaving together a reality that only appears linear when seen from within. And perhaps faster-than-light motion doesn't create paradox. It merely exposes the deeper structure beneath. But think about what it would mean for you personally. If you could travel backward through time, would you? Would you risk erasing yourself for a glimpse of a moment lost, to see a loved one again, to fix a single regret?
Even in the silence of theoretical physics, that question lingers like a heartbeat.
Because what we truly crave isn't to rewrite the past, it's to understand it, to make peace with the flow of time. Maybe that's the hidden lesson behind the speed of light. Not a wall to break, but a rhythm to listen to. A reminder that time moves as it must, and that within its limits lies the meaning of everything we are. Still, one can't help but wonder, if messages could truly move faster than light, what would we hear whispering back from the future? Imagine one morning, your receiver picks up a signal that shouldn't exist. It's faint at first, distorted, almost like static. But as it stabilizes, it resolves into something impossible, a transmission containing data from the future. What would you do? Would you listen? Would you trust it? This is the heart of the next paradox, faster-than-light communication. The idea that messages, not ships, could leap across time. In ordinary life, information is bound by light. It takes just over 8 minutes for sunlight to reach Earth, hours for a signal to reach the edges of our solar system, and years for the nearest star.
That limit feels absolute.
But if you could send a pulse faster than light, you wouldn't just beat distance, you'd beat time itself. The logic is cruelly simple. In one observer's frame, the message might leave after it arrives. In another, it might return before it was sent. The same transmission could appear as both cause and effect, a message that writes itself into existence. And yet, humans are storytellers. We can't help imagining it. What if a scientist centuries from now discovered how to encode information into particles that move through space-time itself, tachyonic messengers? What if they decided to send warnings, discoveries, or even memories backward to the present? The idea isn't just fantasy. In theoretical physics, there are legitimate thought experiments exploring closed information loops. A message could, in theory, stabilize itself in history by ensuring its own creation. A physicist receives a formula, publishes it, and that publication becomes the reason it was sent. The loop closes with the Alcubierre paradox resolved, but these solutions often come at the cost of freedom. In such a universe, choice becomes an illusion. You send the message because you already did. The future dictates the past as much as the past shapes the future. It's deterministic, elegant, but unnerving. This is why physicists say that superluminal communication would collapse causality. It's not that equations fail, they still function, but the story breaks. Who caused what? When? Why? The chain of events loses meaning. Even so, there are fascinating loopholes, phenomena that dance on the edge of this rule. In quantum mechanics, entangled particles appear to know each other's state instantly, no matter the distance. If one spins up, the other spins down. Faster than light could travel between them. But the catch is, you can't control which outcome you get. It's random. You can't send a message this way because you can't choose what to say. It's connection without communication. Still, it feels like a whisper of something deeper, as if the universe is reminding us that separation might be an illusion, that distance and time are just projections of something more fundamental. Now imagine, just for a moment, that someone did crack the code. You're sitting in a quiet observatory and the receiver flickers. The signal comes in pulses, like not random but deliberate.
Maybe it's coordinates, maybe a simple phrase.
Or maybe, chillingly, it's your own voice. Older, weary, recorded decades from now. It says, "Don't build it. Would you obey? Would you dare to change what's already written? Or would you dismiss it as a trick of noise, another false promise of the cosmos?" Perhaps that's why, despite all our imagination, we've never found proof of faster-than-light messages. Maybe the universe doesn't allow them, or maybe it does. But those who send them are bound by a rule we can't perceive. Because if such signals existed, they'd already be here. We'd be living in a world subtly edited by our own descendants, a world that always was and always will be shaped by what must happen. And maybe that's the true irony. The only way to keep time consistent is for those messages never to arrive. Yet in the quiet spaces between static, in the rhythm of radio waves and the pulse of stars,
one can almost feel the longing, a universal desire to reach back, to reassure,
to whisper across the gulf. It's all going to be okay. Maybe someday, that's the message we'll send, not to alter history, but to remind it that we were here, listening, dreaming, and waiting for light to catch up. When we talk about faster-than-light travel, there's one question that inevitably follows, whispered beneath every conversation about warp drives and wormholes. What if someone else has already done it? It's a haunting thought. Because the universe is old, 13.8 billion years old, countless stars have burned and died long before Earth even formed. If intelligence can arise here, why not elsewhere? And if it can, what might a civilization millions of years older than ours have achieved? This leads us to the Fermi paradox, the eerie silence of the cosmos. With billions of galaxies, each filled with billions of stars, it seems almost impossible that we're alone. Yet, as our telescopes stretch deeper into space, we find no definitive signs of life, no signals, no megastructures, no interstellar visitors. Unless we've been looking the wrong way. What if advanced civilizations have found the key to faster-than-light travel? And the reason we haven't seen them is because they exist on timelines that move beyond ours. Imagine beings who can fold space, cross galaxies, or step outside the flow of time entirely. To them, our world might appear frozen like a snapshot in cosmic amber. They could travel past us, unseen, their technology operating in dimensions we can't yet perceive. In some corners of astrophysics, there's even speculation that UFO sightings, those unexplained aerial phenomena, might be glimpses of such civilizations, operating through space-time distortions. It's a wild idea, but not entirely impossible. A warp bubble, for instance, would bend light around it in strange ways. To us, it could appear as an object accelerating instantly, vanishing, or splitting into two. Even the James Webb Space Telescope, JWST, with its magnificent sensitivity, may one day detect anomalies that hint at engineered cosmic structures, Dyson spheres around distant stars, energy signatures inconsistent with natural physics, or distortions in the fabric of space that defy gravitational explanation. But suppose for a moment that such civilizations do exist, and that they travel between stars, slipping through folded space faster than light. Would they reveal themselves to us?
Probably not.
The energy cost of superluminal motion is so high, the control of space-time so precise, that any species capable of mastering it would see us as we see microbes. Delicate, curious, not yet ready to comprehend, and perhaps they have an unspoken rule. The cosmic prime directive, if you will, not to interfere with civilization still bound by the light barrier. After all, what happens to a species when it learns it's not alone, that the universe is populated by beings who can cross time as easily as we cross oceans? Would it inspire us?
Or break us?
Some scientists suggest a subtler possibility. Maybe we have been contacted, not through messages or visits, but through inspiration. Perhaps the recurring dream of faster-than-light travel isn't ours alone. Maybe those thoughts, warp, wormholes, tachyons, are faint echoes, ripples of knowledge filtering backward through space-time from civilizations that already know the way. It's poetic, isn't it? The idea that our curiosity might be seeded by our cosmic neighbors, that imagination itself could be the universe's way of teaching us through resonance. But even if we are alone, the desire to reach beyond light unites us with something greater. Every night when we stare at the stars, we're participating in a dialogue as old as existence. The silence we hear might not be emptiness, but patience. Perhaps the universe is waiting for us, not to conquer speed, but to understand meaning. Because only when a species learns to travel inward, to understand its own time, its own light, will it be ready to move beyond it. And when that moment comes, when humanity finally learns to fold space-time as effortlessly as thought, maybe we'll look back at this era, this fragile age of wonder, and realize that the stars were never distant after all. They were always within reach. If reality hasn't yet given us faster-than-light travel, fiction has. For generations, stories have carried us across galaxies long before science could. From the shimmering corridors of Star Trek's Enterprise to the hyperspace lanes of Star Wars, to the haunting beauty of Interstellar's wormhole, imagination has been our first starship. And maybe that's no accident. Because in the absence of proof, fiction becomes a kind of laboratory, a place to test not the physics, but the meaning of going faster than light. In Star Trek, the warp drive is not just a piece of technology, it's a metaphor for optimism. Humanity, united under one flag, ventures beyond Earth to explore and understand, not to conquer, but to connect. The warp core hums with antimatter power, bending space-time at will, a symbol of what cooperation and curiosity can achieve when fear no longer rules. In Star Wars, hyperspace is chaos and poetry. Ships vanish into streaks of light, then emerge in another system. A visual symphony that turns physics into myth. Faster-than-light travel there is freedom incarnate, but also danger. You can outrun anything, except destiny. Then there's Interstellar, which threads the needle between fiction and physics. Its wormhole near Saturn, shaped by Kip Thorne's equations, is one of the most realistic depictions ever filmed. Watching the Endurance glide through that shimmering sphere, space curving like liquid glass, we glimpse what Einstein's geometry might actually look like. And we feel both awe and dread. 'Cause for every doorway to another galaxy, there's the fear of not returning home. Even science fiction's darker visions, Dune's fold space, The Expanse's Ringgate's 2001 Stargate sequence, remind us that travel beyond light is not merely about speed.
It's about transcendence.
Each story suggests that to master space-time is to touch the divine, to glimpse something beyond the human mind's horizon. But what makes these stories endure isn't just their spectacle, it's their humanity. Every faster-than-light engine, no matter how advanced, is really powered by longing. The yearning to reach beyond isolation, to find meaning in the infinite. Fictional captains and explorers mirror our oldest instinct, to leave home, not because we must, but because we can't help it. And, in a quiet way, these myths prepare us for reality. The same children who grew up watching warp drives and wormholes are now the physicists, engineers, and dreamers trying to make them real. NASA's warp field tests, quantum communication experiments, gravitational wave detectors, they all began as stories whispered through glowing screens. Science.
Fiction gives us permission to imagine before we understand, to live for a while in the what if. And sometimes
that's enough to guide us toward the real thing, because history shows a pattern. Every great leap of technology began as something impossible. Flight, electricity, the atom, each one first a story, each one dismissed until suddenly it wasn't. So maybe when people write or film ships jumping to light speed, they're not escaping reality. They're training it. They're shaping the questions that science will one day answer. Perhaps someday the line between fiction and fact will blur entirely. The hum of a warp core won't be a sound effect, but the quiet rhythm of a real engine pulsing beneath our feet. And when that happens, when the first human ship folds space and crosses the gulf between stars, we'll owe that moment not just to equations, but to the storytellers who dared to dream of it first. Because faster-than-light travel has always begun in the same place, in the stillness before sleep, when imagination stretches beyond reason and the stars outside your window feel just close enough to touch. There's a quiet moment that arrives after every grand theory, every burst of imagination, the pause where we step back and ask, should we? Because faster-than-light travel isn't just a question of physics, it's a question of philosophy. The speed of light, 299,792 kilometers per second, isn't merely a number. It's the rhythm that holds the universe together, a constant that defines what it means for anything to happen before or after.
it binds the dance between cause and effect,
between existence and memory. To break that rhythm is to tamper with something sacred, the structure of reality itself. Philosophers have long been fascinated by the idea of limits. We often think of them as walls, obstacles to be broken. But sometimes limits are what give meaning to experience. A song without an ending isn't music. A life without boundaries isn't living. It's chaos. So maybe the cosmic speed limit isn't a punishment. Maybe it's the universe's way of giving shape to wonder. If we could go anywhere instantly, what would discovery mean? Would awe survive if nothing were distant, if the night sky held no unreachable stars? There's a strange beauty in the slowness of light, in the fact that when we look up, we're seeing the past. Every star, every nebula, every galaxy is a time capsule. The universe doesn't show itself all at once. It reveals itself gradually, like a story meant to be savored. In a way, light speed keeps the cosmos poetic. It ensures that mystery always stays one step ahead of comprehension. And perhaps that's why, even as we dream of breaking that barrier, part of us resists. Because if we ever succeed, we'll also lose something. The quiet patience of discovery, the humbling realization that some journeys must unfold slowly to be understood. Still, the yearning remains. The human spirit has never been content with boundaries. We've always wanted to see what lies beyond the next horizon, even if it means risking everything we know. Yet every horizon, physical or philosophical, demands responsibility. If we ever master space-time, if humanity learns to bend reality, what kind of beings will we be by then? Compassionate, wise, or reckless, still chasing power without purpose. Maybe the reason the universe sets such impossible limits is because it's waiting for us to mature, to match our technology with our consciousness. Faster than light travel isn't just a test of engineering, it's a test of ethics, of humility, of soul. After all, speed without understanding is just escape. And maybe the true goal isn't to move faster, but to move deeper, into awareness, into empathy, into meaning. Because the more we learn about the universe, the more it reflects us back at ourselves. Every theory of space-time is also a mirror, showing us not just what we can do, but what we are. Perhaps that's the final lesson of Einstein's limit, that enlightenment, like light itself, doesn't rush. It travels at the speed of understanding, and when we finally learn to listen to that rhythm, to walk in step with the cosmos,
instead of racing against it, we might realize we've already crossed
the only barrier that ever truly mattered, not the speed of light, but the speed of awareness, beyond every question of science. Beyond every paradox of time, there waits a final horizon, the horizon of light itself. It's not a wall in any ordinary sense. It's a boundary of perception, a place where the known dissolves into the unknowable. Every photon that reaches your eyes tonight has traveled across that divide, bearing messages from the past, from stars that burned long before humanity ever looked up. But there are regions of the universe whose light will never reach us. They are expanding away faster than light itself, carried by the growth of space-time. Beyond that cosmic horizon, there is darkness. Not emptiness, but mystery. And maybe that's where our story of faster-than-light travel truly belongs. Not as an achievement, but as a longing toward that unreachable beyond. If someday humanity masters space-time, if we learn to fold, warp, or tunnel through the fabric of the cosmos, what we'll really be touching isn't speed, but understanding. We'll finally stand face to face with the architecture of reality, the woven geometry that binds space, time, energy, and thought into one elegant continuum. Picture it. The first true faster-than-light vessel drifts beyond our galaxy. Behind it, the Milky Way glows like a spiral of silver dust. Ahead lies intergalactic space, a sea of faint blue and violet, punctuated by lonely stars and the ghosts of galaxies half swallowed by expansion. The ship hums softly, wrapped in a bubble of bent space-time.
Inside, the crew stares at the instruments, but none of it feels real.
They are moving faster than light, yet time flows like a whisper. Through the viewing port, the stars no longer twinkle. They sing. The distortions of light form waves, cascading colors not found in any spectrum, ultraviolet woven with gold, cosmic rays bending into soft hues. Every motion feels suspended, every sound a vibration of existence itself, and then something profound happens. As the ship crosses deeper into intergalactic darkness, the boundary between inside and outside begins to blur. The universe no longer feels distant.
It feels alive.
The fabric of space-time and that silent ocean seems to pulse with awareness. Maybe that's what lies beyond light. Not faster motion, but higher connection. A realization that every atom, every photon, every heartbeat is part of one continuous field, timeless, infinite, aware. Because the deeper you go into the study of light, the harder it becomes to separate the observer from the observed. Quantum mechanics teaches us that measurement, consciousness, shapes reality. Perhaps to go faster than light is to move not through space, but through states of being. And maybe the civilizations that once dreamed this dream before us didn't build engines or warp fields at all. Maybe they learn to travel by thought, by harmonizing with the vibration of space-time itself. Not technology, but transcendence. When you think about it, light has always been the bridge between knowing and mystery.
It's what gives shape to the universe, yet it forever outruns us.
It defines distance, yet it also defines connection. To chase it is to chase meaning, and perhaps that's the point. Faster than light travel may never be about leaving home. It may be about realizing that home was never confined to one place, that every star we see and every particle we are has been communicating through light since the beginning. And that, in some sense, we've been traveling together all along. So tonight, as you lie there listening, imagine this: somewhere in some distant galaxy, another being looks up at its own night sky and wonders the same thing. What if we could go faster than light? And maybe, across that endless ocean, your thoughts and theirs are already meeting. Two waves rising and fading on the same eternal sea. Because beyond the horizon of light, there is no distance, there is only wonder. Now let your thoughts soften. The questions can rest for a while. The hum of the universe, the pulse of stars, the slow turning of galaxies. They've all been here long before you, and they'll remain long after. You don't have to solve them tonight. You only have to listen. Feel your breath align with that rhythm. Slow, steady, cosmic. Each inhale pulls starlight from the edge of time, and each exhale returns it. Part of the great exchange that keeps everything alive. The boundaries between you and the universe dissolve, like ripples blending into a single sea. Maybe faster than light travel isn't about escaping distance, but finding stillness. Maybe the true speed of the cosmos is silence, the kind that carries meaning without motion. As you drift, picture yourself floating between galaxies.
No engines, no sound. Only the soft vibration of existence itself. Every heartbeat echoes through the stars.
Every photon bends gently around you. Out there, beyond light, time has no power. There's no past to regret, no future to chase. Only the endless present, vast and gentle. So rest there, traveler. Let the weight of curiosity fade into calm. The stars will wait. The light will find you again. And somewhere, across that infinite ocean,
a quiet truth shimmers, that you are part of the same mystery you've been trying to reach all along. Sleep well,
dream softly, and remember, every night is another journey beyond the speed of light.